已解锁，请取出话筒。
Testing. Okay. My voice haven't worked out. Okay. Good morning to everyone. So how's the lecture notes going on? Okay. So when do you done? Okay, because I need to print it also. Yeah, I'll print one copy for you, okay, for the test. And for this week revision, supposedly is Lydia, right? Let me check. So supposedly is Lydia. So can we move Hongri up or not? I move you up. Okay. Because I think the last few weeks, right, is about homology. Depends on whether, I guess, see first if I want to include in the exam or not. For the homology part, I have written lecture note for the first section. I'm still writing for cut product, and then we hope to finish at non-correct duality. Yeah, this is our goal. For now, I think our lecture note is about 1,000 slides already. See how it goes. And thank you for the feedback from last week. So I have added things for CW complex. Sorry, delta complex, not CW complex. CW complex was weeks ago. For delta complex, if you still remember that we defined the standard n simplex with the coefficient sum to 1. Okay, maybe you might think that this is a very weird thing to do, but if you still remember how you describe a line, okay, how you describe a line is the coefficient is 1 minus x and x, so their sum is actually 1. Okay. Yeah, and then another thing people talk about was about this hyperplane definition. Yeah. Okay, so we define n simplex with an order. This order has to be transitive, obviously, to be the smallest convex set in Rm containing n+1 point that do not lie in a hyperplane of dimension less than. Okay, so meaning they could only lie in hyperplane that is greater or equal to n. Okay, so what does this mean here? So actually this means that these points are actually finally independent. So yeah, so it means that this hyperplane must at least span by this n+1 point here. Okay, at least span by this n. Not span by n+1 point, but their difference. Okay, their difference are linearly independent. Okay. Yeah, so the picture is like this. Okay, for example, you pick a 4 points in R3 here. Okay, when are they linearly independent? Is when they are sorry. In this case, they are not coplane, yes, because plane is a hyperplane of um, degree less than 3, right? Okay, so here is a hyperplane of degree 3 here. So, or sometimes we call this a generic position. Right, this is a generic position for points. Sorry, did I? Okay, okay. So this is a generic position for 4 points here. So they are finally independent. Another way to see it is their difference is linearly independent. I mean the difference vector, meaning you take v1 minus v0, v1 minus v2, v1 minus v3. They are linearly independent. Okay. This you can prove it. So the third condition I gave last time, right? I guess this is an extra condition. And for now, I think one and two is pretty important for you to see. Okay. Anything I want to update here? I think there's one more. Oh, there's one more. About this open simplex here. So last time we had problem with the point, right? The point. Okay, so what's the boundary here? So last time we asked about what's the open simplex for delta 0. Okay, delta 0 is delta, sorry, the interior of delta 0 is delta 0 take away the boundary point. So the claim is the boundary of delta 0 is empty. Because you need to understand how we define boundary here. Do you still remember how we define boundary for n simplex? We define it as a union of faces. Then do we have shape here? We define as a union of faces. But how do we get faces? We just simply throw away one of the vertex. Okay, so for example, this is a delta 0, 1, 2, delta 2, right? Okay, we just throw away one faces, one vertex, there are 3 possibilities. Okay, so these union together is the boundary. Make sense? Make sense? Huh? Okay, this 3 line here is the boundary of this um, delta 2 simplex. So if you just have one point, you throw away that point, then your boundary is empty. Okay, so by definition, the 0 simplex is actually open. Okay, by definition, it's open. Okay, by definition, it's open. Okay, so we have this funny notation here. Delta 0, interior of delta 0 is delta 0. 可以 Okay. I don't know why. Maybe always when I see this notation, I think about the clown in the function. Oh, there's a news that Japan volcano erupted, I think yesterday night. Yeah. 而且都有3次 ，OK。Okay. Yeah. Oh, another thing, one more thing. Okay, one more thing is this RP2 here. Okay, so last time we say that these three are the three possibility that you can put possible orientation on one simplex. Okay, that you can put on this square here. Okay, so RP2 here actually there's a very intuitive explanation on why we put opposite side on 4 side here. Okay, because what is RP2? RP2 is a set of line through the origin in RG. Okay, so you need to identify opposite point or antipolar points. Okay, so in this case here, actually you are identifying the antipolar points here. Okay, is it V and V opposite and W? And then if you draw all the antipolar point, right, you will see that the orientation is opposite on opposite side. That is. Okay, so it's really opposite identification. Okay, makes sense. Okay, so the direction on top and bottom and the mirror are opposite. Okay, does it make sense? Yeah. So you can think of this as a circle as well. Just there, make a corner for them. Okay, yeah. Mm-hmm. 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 Yeah. This identification is done on the, you can done it on the XY plane and on how you see the RP2, but if you pick equivalence classes for the positive X, right? Then this identification on the boundary is done on the YZ plane. Okay, so this part is the YZ plane. If the inside is a positive X. I don't know. So X here, Y here, Z here. So your boundary lie on the that one plane. Okay. Okay. Right. Okay. Any other question you want to ask from last week? I think this is what I wanted to say. Any other question? No? Okay, if not, we were going to go into our very powerful machinery today, which is chain complex. Okay, so this is, I think, this is something that you've never seen in your mathematical life before.
No, we'll see.
Oh, that's bad. Okay. All right. So let's do some recap. Yeah, let's do some recap. Recap what? So basically, what's chain complex? So let's take CI's a group, or rather free abelian group. Why we talk about free abelian group here? Really, we care about modules. Okay. Free abelian group. And then we will arrange them like this. So C2, C1, C0, C blah blah. Okay, decreasing. So the arrow is going to decrease. So this is pretty important, this arrow and this labeling here, because in the homology part, we will swap the order of the arrow. Okay, meaning small to big. Now it's big to small. Okay, so this is like a descending. And then between these group here, we got a map. So we also label by number. Okay, label by number. And we require that dn plus 1 on dn is 0. Okay, so what's the significance of this is this will make sure that the image, okay, this will make sure that the image, did I do this the wrong way or not? Okay, I'm good. Oh, this one is not good. This one the wrong way. So we should go from the big one to the small one, right? Okay, so we do the big one first and then we do the small one. But this will implies that the image of dn plus 1 actually is in the kernel of dn. Okay, this is very important. Why? Because later we're going to form some coset here. Okay, so this coset here is actually kernel of dn over kernel of, sorry, image of dn plus 1. Okay, only you have this subset inclusion here, you can form the coset. Make sense or not? Otherwise, you cannot just quotient it because you might contain something else. Okay, make sense? Okay. So this is about good theory. Okay. And then this hash n here is what we call the homology, okay, or the n homology of the chain complex. Let's see. So maybe we call this a chain complex. And this chain complex comes with data of differential. Okay, so far so good. Yes. Huh? Yeah, this is called a differential. What's differential for you? Differential form. What kind of differential? We call this kind of method differential. What do you think about differential? dy dx? Yeah, you could think like that. There's a theorem called Homology then. Too far. Okay. those are type of differentials. Huh?
You mean
The dx dy, yeah. Those are differential as well. They will satisfy some chain complex as well. But that one will be in cohomology. Yeah, they will become some kind of ddx is 0, if you know that. ddx is also 0. Yeah, ddx is 0. Yes. If you take differential manifold, I think you will reach it at the end. Yes. Yeah, ddx is 0. Maybe we'll converge in the end. See. So what else? Yeah. Any question for now? And then actually there's one free abelian group you met before, right? Last time, which is we can take this C0 to be like the delta, what's our notation? The n chain, delta 0 like that. Okay. So maybe we can take Cn to be delta n. Is this our notation for n chain? Let's check. Yes. Okay. So like this. Still remember what is delta nx here? This is some linear combination. Okay, just some finite linear combination. Okay, on our n simplex. What's our notation for n simplex? Delta sigma. Is it sigma? Delta me? Maybe sigma. Maybe put sigma. Okay, sigma. Okay, so finite sum. So this sigma I is like maybe I write down the form of sigma I. So sigma I is equal to like V V vi 0, vi 1 up to vi and minus 1 like that. Okay, just linear combination. Okay, so you might wonder what kind of D I can put on it. Okay, what kind of D we can put on this thing here. So what kind of D we can put on it? Okay, what kind of D we can put on it? Later we'll see some example of what kind of D we can put on this chain complex. But this is not too far from our motivation last time, where we just look at the, for example, if for one simplex, we just look at the orientation, right? So when it go up or go into a vertex. Okay, so before going to example, we have one very obvious thing to see. A very obvious thing, if the boundary maps in a chain complex are all zero, then the homology group of the complex are isomorphic to the chain groups then. So this one makes sense or not? So if you write it up, so if you have like C0, C1, C0, C minus 1, and then blah, blah, blah. And then the map is 0. So what's the kernel of a 0 map? The chain group itself. And what's the image of the 0 map? 0. So you take the chain group mod out by 0, so this is the chain group itself. Okay, so this is a very nice chain complex. Yeah, the chain complex will reflect its homology group. Okay. Next, okay, let's do some example. Okay, let's do some examples. Let's compute the homology of next one. Okay. So to do this, we need to know about the n simplex, right? So meaning we need to give a delta complex structure to it. Okay, so what is the delta complex structure we want to give to it? So we will consider the easiest one, which is you take a point and then you take a one simplex, glue around it. Actually, this is also the CW complex structure we'll give, right? Okay. Right. So then let's see what are the chain group we get here. So let's write down some chain group here. So let's say here's 2, here's delta 1, here's delta 0, here's delta minus 1. Okay. So this is I don't know this is a working or not, but at least this is what we do during our research. We will label the degree of this chain complex. You can follow this or you can build your own convention, but as long as you put in the right place, you are good. So that's most of them are empty. Okay, most of them are empty because in this space here, there's really only 0 simplex and 1 simplex here. Okay, so for most of the places, they are 0. 没有。Yes。一边也是 labeling，另外一边也是要符合 definition，但是 by convention 我们就把它想成 empty。So you can okay. So actually something you can infer from here is if we consider if we consider delta complex, right? The delta negative will always be empty because there's no negative dimension of simplex. Okay, so where's empty? So that means it's only one-sided. This sequence here is not going both sides. One side is always 0. I define it to be doubly sequence because and just make it more general. Okay, so there are two things here, right? So let's call this point V. In that case, delta 0 is a linear combination of V, and then delta 1 is linear combination of E. Okay, like that. Make sense? Okay, so what's the map we should put here? Okay, what's the map we should put here then? Okay, so, well, I mean, these two map is obvious. 0 to something or something to 0. There's really one thing you can do. Okay. But here, what should we put here? Okay, something that makes sense. Okay, this is, we were going to define this to be E sending to the end point minus the starting point. Okay, end point minus starting point. But these 2 points is the same in this case, so it gets sent to V minus V. But V minus V is 0. So actually, this is a 0 map. Okay, this is a 0 map here. Okay, so just now we talked about what if a chain complex is all 0 map, right? Okay, so meaning what? Okay, so we can compute this homology here. So let's denote this homology as H delta coming from this. Okay, so there's really only Z, okay, for n equals to 0 and 1, and then 0 for the rest. Okay, so there are two homology here, non-zero homology. Okay or not? Okay, so if you want to compute the 0 case, you need to take the delta 0 over kernel of delta 0 over the image of delta 1. And then if you want to compute H1, you take the kernel of delta 1 over the image of delta 2. Okay, for these, they are all Z because this is isomorphic Z. So A of that B. Okay. Yes.
Is it isomorphic to Z?
You can build this isomorphism, right? Send V to 1. Mm-hmm.
Isn't delta 0 set for
Mm-hmm.
it just contains B, right? Why do we
No, linear combination of V. Free abelian group. So that's why I put a ZV here. Linear combination of V. Linear combination of V. It's just V, then this is just a function, no homomorphism. It's a linear combination. Linear combination. 2V, 3V, 4V minus 2V. It's all inside there. Okay. Yeah. So meaning we actually put a module on top of this point here. Okay. We put a module on top of this point. Put a free abelian group on top of this point, this object. I can tell you what's the geometric meaning of this non-zero homology group here. Okay, so maybe later we will deduce it. So for now, what you see is, as in the motivation, if there's non-zero, for example, in a H1 case, there will be a hole, a one-dimensional hole. Okay, so you can actually see a one-dimensional hole. Okay. How about H0 then? Okay, H0 actually is something related to path connected component. Okay, so if you look at this S1, right, there's only one path connected component. Sorry. One more topic. Yeah. Pi 0, you mean? Yeah. Okay. I think we will deduce it, or at some point we'll see it. Yeah, let's continue. Let's do one more. Second, let's do the torus. Module of torus. Or do you want to guess? Want to guess? Any guess? Huh? What? Any guess? Okay, let's do it. Yeah, you need to learn to guess, because you need to learn to conjecture. Conjecture is something very important. Is this a torus? I think this is a torus.
他们感觉不太可能猜得出来。
可以啊，等一下我们来理解这个答案。Okay, so this is the torus we've seen last time, but it is not delta complex yet, right? Maybe it's a CW complex. Because delta complex, you need a bunch of triangle. Okay, you need to what we call triangulate your manifold. So to triangulate it, we need to produce a diagonal line here. Okay, let's call it C. Okay, to produce this, you cannot simply choose orientation, right? Last time, remember, you need to keep your vertex in the right order. So that there's a order of vertex here that makes sense. Yeah, for example, here we have like what is it like? Oh, all of them is V. Yeah. Okay, in this case, well, should I rename them first? So if I rename them like V1, V2, V0, V1, V2, and then on the other side, here we should put V2, here should put V3. Makes sense. Okay, so we got like the two simplex as in V0, V2, V3, and V0, V1, V3. Okay, if you try to turn this around, then it might not make sense. Okay, you can try and turn it, see if you can put a proper order on them. Okay, so in this case here, there are three part that's non-zero. Okay, so we have delta 2, delta 1, and delta 0. Okay. So you can see that this one, zero simplex here is just one because for 4 of them, we have already identified them. Okay, we already identified them. And then it will be 0 onward, below -1, and above 3. Okay, let's call the two simplex, one of them U and the other L. Okay, then I think we have enough label here. So we have 2 delta 2, and then 3 delta 1, and then 1 delta 0. Okay. So we need to figure out what's their map. Okay, what's their map here? So again, similar thing. For delta 1, we just compute their endpoints. Okay, the in and out endpoints here. So as again, just 1 point, so V minus V. How about U and L? How about U and L here? Okay, how about U and L here? How about U and L here? Also, we choose the orientation for them. Orientation like that. Okay. So after we choose orientation for that, then we'll see how this U and L interact with the orientation of the simplex. Okay, so for U, you go A, B, and then the other way of C. Okay, so A, B, minus C, like that. Okay, and then for the other case, what do you get? Am I doing the right thing here? Okay, minus C. Let me think. Why my L choose the other way around inside my note? Huh? What do you mean? Well, link 是什么意思? You want to compose both to be 0? So in my notes, right, I tend to choose this direction. But why? Okay, I choose both. Maybe both will work. See, why you might not choose the other direction? Any problem or not? Let me think about it.
一定要把人数量
不是 I guess on this I guess because this direction, I think these two directions should like how to say compatible with each other. You get what I mean or not? Let me think. Okay. I think what you should think about is you should put an orientation on your real torus here. Okay. So if you already fix one orientation, right? I think the other direction is already fixed for you. Does it make sense or not? Like you cannot be like put orientation different way on the other side of your torus. Yeah. I mean the other side meaning this way. This way is a different way, right? One is anti-clockwise, one is clockwise. So I think across this C, you should put the same orientation. Okay, so same orientation means you need to use the same clockwise or anti-clockwise direction on both sides. Does it make sense? Does it make sense? So maybe let you compare these two here. Let's say this line is C. Okay. I think C cut across the whole torus, right? C should cut across the whole torus. Okay, so actually it's this orientation here. If we put this orientation here, actually is also A minus C plus B. So these two are the same thing. Okay, so basically this orientation fix our differential here. So to make sense of this, you need to check whether these two composite to 0 or not. Okay, these two actually composite to 0. Why? Because A, B, C itself will get sense to 0. So 0 plus 0 minus 0 is 0. Okay, so actually it's a differential map. You might think that, well, very intricate, huh? Very dependent on our delta complex. This is very true, actually. This is very true. So maybe you can ask the question, right? For example, x1, I can build my x1 using two zero cell, or two delta 0 and one x1. Do they get the same homology or not? I invite you to compute yourself. They do have the same homology. Okay, I invite you to compute yourself this example here. You use the same setup. Okay, the endpoint, difference of endpoint, and then try and compute the homology. You get the same thing. Okay, although you started with a larger vector space or larger module, but you will get the same thing. Okay, and this is something that is not proven in Hexer. Meaning, if you change CW complex structure, do you get the same complex? But instead, later we'll move on to something called singular homology. Okay, let's continue to compute this first. Well, so how to compute this? So let's do H1. Okay, so what's H1 here? Okay, so let's see. What's inside the kernel of delta 1? Okay, what's inside the kernel of delta 1? Actually, you are three-dimensional, right? Three of them get sense to 0. And then what is the image of delta 2? Okay, image of delta 2, there's only one, right? A plus B minus C. I mean, spanned by this element. Okay. Anyone know how to compute this? Actually, this is a quotient of a module, or quotient of a vector space. Have you guys learned the quotient of vector space before? No, only learn quotient group, right? Okay. So how to do this? This is a bit different from ideal. Okay, don't simply cancel. I warn you first. This is a bit different from ideal. So make sure you have the same basis first, and then you do the cancellation. Okay, so you can see that these two bases, these two spaces in the numerator and denominator has different bases, right? Okay, but can we produce similar bases or not? We can. Okay, we can. Because the top one, we can do a change of basis to z of a, b, a plus, b minus c. Okay, and then quotient out by the scalar multiple a plus b, c. Okay, in this case here, any linear combination involving a plus b minus c will goes to 0. Okay, so then this will get z of a, b, which is z plus c. This is h. Okay or not? Okay, please don't use the ideal way to cancel. Please don't think wrongly. This is what do you mean? Difference of what? The ideal. This is a quotient of module. This is not a quotient of ring. This is a quotient of modules. It's a bit. It's different. It's different thing. Yeah. So maybe you want to ask what's the difference between generators and bases. What's the difference between generator and bases? Yeah, on ring, on a group, we talk about generators, but in a module vector space, we talk about bases. So what's the difference between generator and bases? Generator can multiply generator, but here, there's no multiplication between generators. I mean bases element. Okay, so please be careful. You need to learn some change of basis technique here. Okay, next one. How about H2 here? So how about H2 delta? Is the kernel of delta 2 over image of delta 2. So what's the kernel of delta 2 here? So, well, I mean, can we write down this in terms of matrices? Because these are free abelian group, which are modules, right? So you can think of module as a vector space, or actually map between finite dimensional vector space or finite dimensional module. You should have you can express it as a matrix transformation, right? Okay, the first year material here. So what do you do here? Actually, you send it to this matrix 1, 1 minus 1. Both component U and L get sent to the same place. Okay, 1A, 1B, and minus C. So 1, 1 minus 1. Okay, so if you compute the kernel of this, what do you get? I mean, you can do row reduction. And what you get is one-dimensional kernel, which is U minus L. But obviously, you can see from here as well, U minus L should be inside the kernel because they both sent to the same place. But why is it the only one? Then you need to prove. Although, why is it the only one? My proving is row reduction. Okay, you can use row reduction. And then there's no delta 3, so actually this is set. Okay. Yeah, so if we put all these together, what we will get is you got the z plus z for n equals to 1, z for n equals to 0 and 2, and then for the rest, it's 0. Okay, so again, you can link this back to pi n of idea by idea of pi n, which means there's a two one-dimensional hole here, and then one zero-dimensional hole and one two-dimensional hole. So zero-dimensional hole, we think of it as a half-connected component. So everything is half-connected there, so there's only one half-connected component. And then the two-dimensional hole, is the torus itself. The torus itself is a two-dimensional. Okay. The torus itself is a two-dimensional. Actually, there's one way to think about, a very advanced way to think about it. Maybe I can teach you a bit. I'm trying to sell a lot of advanced course here. Okay, one way you can think about this torus, right, is you can take your sphere, okay, and then attach what we call a handle body. Handle body. So when you do some surgery, so you puncture your sphere, and then you attach a handle to it. Then this is the torus. Hmm.
实心的
No. It's a
正设备
just cylinder. Yeah, cylinder.
一直打一个帮我还是打两个帮？
两个。Do I make this doctor as well? This is like you go to gym or not? You go to gym? Yeah, the bell. Handle body. Okay. You mean the intersection between handle body with the sphere? 哪一个？谁的 intersection？谁跟谁 intersection？没有穿过去，就 attach 在上面吧。就是没有穿过去啊，没有来的啊，不是这样子，不是把它包在一起，我只是 attach 一个 handle body 在一起。哈？哦，这样子看来干嘛哈？So 我本来想要解释这个 two-dimensional hole 的，就是 like 就是 on this torus right? How do you see the two-dimensional hole？就是那一片 two cell， 对吗？就是这个 sphere 怎么融进这个 sphere 这个 torus 里面 ？Does it make sense？ Does it make sense? Who makes sense? So like, how did you see two sphere inside here? You see two sphere inside here. 就 I mean like 这一个 ，yeah. How do you see two sphere in a torus? Okay. Yeah, I let you to imagine first. Yeah, let's do one more and then we're gonna take a break here. Next is homology of RP2. Okay, so we draw RP2 and opposite that. And similarly, we have this U and L. See here. Here is W. Okay. Note that the orientation for U and L here should be opposite now because we identify in opposite direction, right? Okay, so there's a opposite orientation that we take here. Okay, let's see. Is this the one we wanted to be? C B minus A, and then C A minus B. Okay. Okay, so the slightly difference here in this case. So what's the slight difference here? Delta 1, delta 2, delta 0. Again, we have ZU plus ZL. And then here is ZA, ZB, ZC. And then the other one, we got ZW plus ZD now. Okay. Right. So in this case here, so if we determine the delta 1 first, so we can see that A and B both go to W minus V. Okay. But C is V minus V, so which is 0. Okay. How about U and L here? So U will go to C plus B minus A. And then L will go to C plus A minus B. So we can write down this matrix transformation here, minus 1, 1, 1, 1, minus 1, 1. And then for the other side, you can write down like 1, 1, 0, minus 1, minus 1, 0. Or 1, minus 1, 1, minus 1, and 0. C gets sent to 0, and W and plus 0 and V. Okay, so here there's some tricky things happening. So let me write down here. So for H0, right? Okay, you have a Z of WV over Z of W minus V. Okay, because there's a non-trivial image now for delta 1. But obviously, you can do change of basis, right? So we can cancel out the basis of built up by W minus V. So this is just a set. And how about H2 here? Okay, H2 here. H2 is what? Kernel of delta 2 over image of delta 2. Should we compute this first? Okay, let's compute this first. Okay. So what's this? Actually, you can try any linear combination, or if you don't want to try, just show that that matrix has a 2 pivot column. Okay, meaning it is injective. Okay, not invertible because yeah, the dimension is weird, but it's injective, so this is 0. Since delta 2 is injective. Okay, you can maybe check by check pivot column. Or can you share away chat? I think you can share away chat, right? This thing. There's what do you call this? There's 2 pivot position. 2 pivot position coming from this one and this one. Either 1 or 2 with 3. Yeah. Okay. Year 1 friendly. Yeah. Year 1 friendly. Okay. Yeah. Then first question, year 1 friendly. Second question, compute the homology. Okay. Okay. How about H1? H1 is a bit complicated, so that's why we left it to the last. Okay, let's look at H1. So H1 is kernel of delta 1 over image of delta 2. Okay, so well, you can go and do your row reduction and stuff like that. But what can you see is, you can see that delta 1, right? There's only one pivot. There's only one pivot because 2 rows are the same. So you can row reduct the second one to 0. And then you have 2-dimensional null space, right? So there are 2-dimensional null space here. So what are them? Well, if you write them first out, I guess you will see A minus B and C. Right? Okay. A minus B and C is one of them because you just try and play, and then you will see that these two are living in the same, living in the kernel, and then they are linearly independent of each other. How about image of delta 2? Image of delta 2. Okay, how about the image of delta 2 here? What's the image? Well, obviously you get A minus B plus C, no? Okay, A minus B plus C. Any other thing inside here? Actually, just A minus B plus C. Right? Is it? Ah, A minus B plus C. Because we said that the kernel is two-dimensional, is it? So image can only left with one-dimensional. That's true. Hey, first year. First year. So just now we said that this is the null space is 0, right? The null space is 0. No, the null space is no. Yeah, the null space is 0. So what? The dimension of kernel is 0. And then, hey, there's one formula, right? Rank of 2, huh? Rank 2. Okay. Yeah. OK， kernel 应该不是零对吗？因为001 is in the kernel, right? Is it? Wait, let me think. Sorry, 我讲错了。What's the rank nullity theorem again? Nullity plus rank equals to what? Equal to the dimension of the domain or equal to the dimension of the domain? Okay, so the domain now only 2, right? Okay, so the dimension of kernel is 0. So meaning the image is two-dimensional. Okay, so what's the two-dimensional image here? So one of them obviously is C plus B minus A. One of them. Okay, the other of them is C plus A minus B. This is two of them. Okay, good. This is two of them. But we can do a little change of where basis. We make it to C and A minus B plus C. Okay. Okay, now it's very dangerous thing happening now. Here is a very dangerous thing. So because they are in different bases, you cannot just cancel. You cannot simply cancel because you need to think yourself. What is this operation here? This operation means what? Top linear combination in A minus B plus C, and then bottom is a linear combination between C and A minus B plus C. Okay, so this identification you cannot just simply do as the ideal case. It's very different thing will come out. Yeah. I mean, if you want to put B minus A plus C also can, but we can do change of basis. Huh? Yes, that's good. That's good. That's the 2C we wanted here. So we want the 2C. Huh?
Why you write this?
We haven't finished. I haven't finished. Like I haven't done yet. I'm not done yet. I'm not done yet. It's just that I'm lazy to put B minus A plus C. But later we need to see as well. Okay. So actually, this is not good because when you want to do quotient of module, right, make sure that they are expressed in terms of the same basis element first. Okay. So what are the same basis element you could have here? So a very good choice to make here is at least make your denominator have A minus B plus C first. Okay. And then at the bottom here, what can you do? Okay, what can you do here? Okay. This C shouldn't pop up, right? It's a 2C here, right? because how I get this here. Actually, initially I thought, wait a minute, let me try. Initially I thought A minus B plus C. I can cancel with this. Okay, I thought I can cancel it with this thing here. Okay, so I thought we can cancel these two things. Okay, it turns out that you will have 2C, yeah. Okay, your worry is correct. Okay, I thought we got only C here. So if we do this chain of bases here, then we have ZA minus B plus C over C quotient out by A minus B plus C plus 2C. Okay. So what does this mean? So this means that on the top you have a linear combination in between A minus B plus C plus something plus C. And then bottom here is a linear combination of A minus B plus C and then 2C with 2C. Okay. So this quotient will tell you that this linear combination at the bottom here will always be 0. Okay. So if you quotient by this, meaning that every two elements in the numerator will be equal by an element in the denominator. Okay. So you can see that multiple of A minus B plus C is always 0. Next is a multiple of 2C is 0. Okay. So in this case here, what you get is actually Z mod 2. Okay. Let's see which is Z mod 2. Okay. Okay, so why is there a Z mod 2 here popping out? Okay, why is there a Z mod 2 popping out here? Actually, this will represent the orientation, okay, on this space. Z mod 2. Z mod 2 orientation. Okay, so where's RP2 here? Okay, any question? Any question? Yeah, this is very interesting space. Yes. Fundamental group of RP2, yeah. Have we computed pi 1 of RP2 before? I think it's Z2, is it Z2? Z2. Why is it Z2? I think we haven't computed before. Why is it Z2? Did we compute pi 1 of RP2 before? Maybe it's a good exercise to do. What's RP2? Did I did it in some tutorial? Not recall now. I think at some point we see it. Yeah, maybe can you calculate this and compare? Yeah, Rachel said this is also that too, right? Please check this. Can't recall now. Yeah, I think at some point we did this. I think I did it in the tutorial because pi 1 of RP1 is something else. It's a bit different. I think this is like Z times Z2 like that. For the rest, yeah, it is. I mean, I need to check. Okay, so for now, if pi one of RB2 is Z2, then for now it's still match up, still match up with our pi one thing. And so this is another reason we learn homology, because for most of the cases, actually, hash n behave the same as pi n for most of the cases. And this is actually easier to compute because this is very combinatorial, where you put triangle, put line. But if you want to consider pi n, right, you need to consider continuous map from S1 or from Sn. Any other question? Okay, let's break until 10:18. We'll come back with singular homology. Hey. Yeah.
这个我不太，这个图是不是那个刚才那个用一些 simplex 来 build，比如讲 AB，
对，
要不然是 BA，好，所以应该是没有问题啦。这个我这样理解可以吗？先 build 一个 A 在这边，A 在下面，在下面，然后画一个圈圈，然后再画一条线再回来。
可以啊，没有问题啊，是这个意思，
是这个意思，
是这个意思。
然后这个上面是 U， 下面是 L。
啊，对。
OK，
对对对对。
还有一个是这个，这个是你的，这个是 S1 现在我有看到一个这样子，它不 homotopy 啊，更准确讲，它是其实根本就不是 homotopy。S1 为什么？
因为你讲 homeomorphic 啊，还是 homotopy？
如果是 homotopy，
homotopy 他们是 homotopy 可分，但是他们不 homomorphic， 肯定不 homomorphic， 因为你都不够，这边只有一圈吧，这边有这么多个圈，它的 bijection 都做不到。
不，应该不是，
你要问什么？
应该是这样子 ，S2。
哦，这样你要问 homomorphic 还是要问
homotopy。
哦 homotopy 可分这样的话，第一你可以从台湾那边看啊，台湾那边看就是说。因为如果 homotopy 可分的话，他们的排完一定要是一样的，所以这个的排完是 set， 这个排完是0，所以他们就不 homotopy 可分。这样的话，你是不是要问我排完怎样算？
排完我懂，就是用那个 S1 乘上这样子，然后它可以把它 split 开嘛，是这样。
哦，也可以，sure，可以 split 呀，可以，你可以 split， 或者你 deformation retract 去 S1 也可以。
deformation retract to S1
啊，然后他们 deformation retract 的 homology 是一样，然后这个排完是0，我们在班上有证过。
是，
所以就一个0一个 Z， 这样就不同的都可以搞。
有想到一个是，我有问 AI 啊，但是讲，在这边上面啊，有一个地方不可以去的，就是如果你要放个 loop， 就是
我不懂，
就是我本来我叫他，我有问他这样子，这样子也是一个 loop 嘛，对不对？这个是一个 loop，
这个你是说
就是把它人切开，
你是说这样绕过来这样
啊？对，从
你说这样这个 loop
啊，
然后呢就是这样这个是 loop， 这个是 contractible loop， 但是我们的意思是我们可以找到不 contractible 的 loop
在哪？
在这里。
哦，
对吧？对呀，
它不是可以收进上面的点吗？
没有，上面没有点给你说，它是空的，空心啊。
这个是空心的
，cylinder 啊，你不是 cylinder 吗 ？X1，
这上面
空啊，肯定空的啊，不然呢？你哪里有可盖下去？你要盖的话，你要拿一个 D 去盖它，你要拿一个 D2去盖它。 你要拿 D2 去盖它才有。
哦，
你自己写啦
对
，S1 全部都是
是
S1 不然的话，
对，
对不对？确实啊，像你讲的，如果盖它的话，然后这个东西 deformation return 去一个点，就是这个东西啊，就是这个顶啊。Yeah，你讲 AI 说什么？它没有一个方向可以去，什么意思？
哎，因为我以为这里面是 fill 掉了，所以我就看不懂他在讲。
我觉得你如果要用方向的东西来解释，我觉得也是不是不可以。就是你没有一个，你没有，这是应该是比较 advanced 的东西啊。就是这个方向不是，这个是有很多方向可以去的。诶，但是这个点也是有很多方向可以去的嘛。
在这上面是
我想一下，哦，OK，这样算了，这样算了。
每个方向都可以投，
嗯，哦，OK，OK，
一直可以。
哦，我明白，我明白。OK，因为你看，在这个圆圈上面哦，你每一个方向都可以走嘛，对不对？但是哦，你在这一个点上面哦，它有一半的方向不可以走，是这样讲，它不会走这样这一塞的东西不会走，
没错。
所以我觉得也可以用这种方向的东西来看，我感觉。
OK，
但是我们这边还没有来讲这种东西，这个应该是比较像 metaphor 里面的东西，因为它是 tangent，但是我觉得有关联，我觉得有关联，我觉得有关联，有关联。
这样子的话，还有一个是这个什么，我看到一个
嗯
我还是有点难以理解。
嗯
比如讲这个是一个，这是一个 field，然后有一条线，
嗯
有 assignment 就看到。他讲这个 A1 其实是减 S 就减掉这个 animal 的 S R，对，它这个东西进来是后面会读 S1 成分，我就看不懂。
等下你在这做么？你这个是这条线来做么？
哎哎，
这线来做么？
这样我就看懂了，
就是破洞吧，嘛，对不对？
我不懂是
就拆掉了。
了解。
了
OK，
OK，
还有一个是那个有一个那个红毛豆比那个有一个 cylinder 的，记得有一个如果 x 跟 y 是 deformation，那就 yeah only if 有一个
哦呀，对，
这个我就没有
这个你不是有抄那个 proof 了没？
不抄了，但是没有明白，
但是没有明白。OK，好，
只是懂它之间的联系，
我
但是
想一下，
做什么？而且
他的意思是说他 OK，x 跟 y 不一定能够 deformation retrace 去互相，但是我可以 build 一个头有 x，一个头有 y。then 他们就可以透过这一个 cylinder x 变到 y，然后再 y 推到 x。
OK，
这个是那个 proof 在做，就是你问我啊，
哎
你不是问我说去哪里，说去哪里没？我就是制造一个比较大的 space，让它可以在这个，它好像那个 mapping cylinder 好像一个开管道这样的，一个是头，一个是尾，x 在头，y 在尾这样，然后 y 可以缩进这个 cylinder 去 x，然后 x 可以缩进这个 cylinder 去 y。
谢谢。
因为我算过排 one 哦，这个 RPN 是，我是算过，忘记了，想不起来。想不起呀，算这个排完嘞。如果我有一个圈圈的话，哦，应该要用 Van Kampen。I think you need to use Van Kampen to compute this RP2 case because we already got the CW complex here, right? So you need to build your Van Kampen. So you can build your Van Kampen around, I think here, the middle of the set and the label epsilon goes around this one skeleton here. And then you use Van Kampen to do it. Yeah, I think it's Van Kampen. It's very familiar. Yeah, I suggest you to try compare the two computation here. A striking result is H1 is actually a abelianization of type 1. Okay, but since this case, type 1, if this is true, type 1 is abelian, then that should be the same. Okay, if not, it's an abelianization of it. So it's an abelian version of that group. Okay. I think we should continue. Okay, let's continue. So to continue, maybe I can use slide a bit. Quickly motivate. So like what we said just now, because we got so many CW structure, we can put on the delta complex or the delta structure along the delta complex. Do they have the same homology group? No. It's not clear actually, not clear from definition. It's not clear from definition. But it is true actually, but I think Hatcher didn't show it. If you have some textbook that show it, maybe you can show to me. But what we're gonna do using a Hatcher approach is we'll go straight into singular homology. Okay, so then here we will answer as long as your two complexes are homeomorphic, then they will have the same homology group. Okay. Okay, so what's singular homology here? So let's start with a singular simplex. Okay, so singular simplex here is a bit harder. It's a continuous map. Okay, we don't just look at the n simplex anymore. We look at continuous map. So continuous map from n simplex to x to the topological space. All right, this is a singular n simplex here. So you could imagine that this space is much larger than n simplex. Okay, much larger. Then we'll form something called a singular n chain here. Okay, instead of n simplex is placed here, we place a continuous map from n simplex to x. So this is a singular n simplex. Okay. So now, okay. Yes. Yeah, so there is a close relation between these two. Okay, when you want to have n simplex inside your topological space, right? You have a collection of map, right? Okay, but here is all possible collection. All possible collection. It's not satisfying those things. Remember, no? That collection of map maybe is restricted to those axial you put down, but here is as long as you have a continuous map, you can put it in. Okay, so this is a much larger set here. Okay, much larger set. Make sense? Huh? So for now, okay or not? Okay, instead of delta n I put here, I put a continuous map from delta n. Okay, so this is the difference here. So you can imagine if I have homeomorphism right between x and y, then all the continuous map into x will be a continuous map into y. Because it's a homeomorphism, then you can go both ways. Okay, so they will have the same n chain. Okay, if two x, y are homeomorphic, two spaces are homeomorphic. Because we just care about continuous map here. Okay, so far so good. Okay, question? Go question. Finite sum is also we also take finite sum just now. See, what do you mean? No, not depending on Cn. Cn here is just controlling the map coming from one n simplex. So here is this I indexing is depend on sigma I, depend on how many singular n simplex you have. And then here we only do finite sum, meaning we don't have like infinite sum, non-stop one. No series here. No question? Yeah, okay. So what's the map you should think about? What do you think? What kind of map makes sense here? Okay, what kind of differential, differential that makes sense here. Okay, so you should think about the differential, what it does. you have to send sigma I that operate on delta n to sigma I that operate on delta n minus 1. So you are lack of one vertex. Okay, so you are lack of one vertex, meaning you should throw away one of the vertex. Okay. So meaning you can consider the boundary map as this alternating sum here, where you just restrict your sigma to the faces. Okay, restrict your sigma to the faces. Then there's an algebraic miracle here is this is a differential. Okay, this is an algebraic miracle. Okay, actually there's a lot of algebraic miracle happening here. Only then this field can grow. Otherwise, how is it topology related to algebra? Okay, so there's a algebraic miracle here is if you compose these two together, again you get 0. Okay, let's talk about why you get this miracle here. So if you do delta twice, right, meaning you throw away two vertexes. Okay, you throw away two vertexes. So maybe we can look at this computation here. So if you throw away one vertex, maybe you just throw away a vi, for example. Then the next vertex you draw is either before vi or after vi. Either before or either after. Okay. So if it is before vi, then you will have a contribution of minus I to the j. Okay, but if it is after, what happened here? You have a contribution of j minus 1. Why? Because I get thrown away already. So I becomes the 0 vertex. Okay, the thing afterwards you need to counter with minus 1. Does it make sense? Make sense? Does it make sense with this j minus 1 thing? Should I write an example? Let's try. So maybe try V0, V1, V2, V3, and V4 like that. Okay, so let's say we throw the V2 out first. And then throw in V1. So here, let's say V1 to the 2, and then here will be V1 to the 2, and then minus 1 to the 1. But let's say we want to throw V3, how should we compute the contribution? Huh? How should we compute the contribution here? Okay, so instead of 0, 1, 2, 3, 4, right, it becomes 0, 1, 2, 3. Okay, you throw the second one. So it's a j minus 1. Okay, so minus 1 times 2, and then minus 1 to the 2, which is equal to 3 minus 1. Does it make sense? Because one of the vertex before it already get thrown. Okay, so there's an alternating sign happening here. So they cancel. Okay, makes sense? There are two ways. Okay, there are two ways to remove two vertex. Okay, and then the other way will cancel with each other. Make sense, huh? Question? Got question? Combinatorics are this one. Got question? Anything? No, not for this. No. Yeah. What do you mean? Finite sum is just finite sum, meaning like any finite sum you could take, maybe like n1 plus sigma 1, sorry, n1 sigma 1 like that. Just stop here. Or you can take n1 sigma 1 plus n3 sigma 3 like that. All possibility. Maybe got 2 sigma 1, 3 sigma 1 also in there. As long as it's finite. This is called finite sum. Okay. Okay, so this form a differential, then we can form a singular homology here. Okay, we can form something called a singular homology because the image is inside the kernel. Okay, so yeah, 区别 the basis here is different, correct or not? The basis here is continuous map. The basis before was delta n. Does it make sense? Here is map of, previously is delta n. Okay, here is function. The basis here is function. Yeah, 不一样，所以呢，this previously was restrict to faces, but here what we do was we restrict the map to these faces. 对吗？这个行吗？ Previously was like this. Now it's like this. 那有看到差别吗 ？Okay. Make sense? Okay. Okay. Right. So there's few remark here. Homeomorphic spaces will have isomorphic singular homology group. This is different from H delta n here because there we need to check. But on the other hand, this group you can imagine is very large. Okay, for one delta n, maybe you can have different continuous map that you can map into it. But this is not the case for delta complex X, right? So it is not clear that why this singular homology will compute to something like what we compute just now. Why Z only? Why maybe just Z plus Z? Because the finite sum we considered just now was like across all the continuous map, right? Maybe there are uncountably many continuous map. So you might imagine, oh, I need to coefficient by infinitely many continuous map as well. Okay, so that our homology group is finally generated. Okay, but on this remark, the simplicial homology is easier because we only need finitely many n simplex to work. So from that side, it's clear that our homology is finally generated. But for singular one, it's not very clear. Okay, for singular one, it's not very clear. And so there are advantage and disadvantage between these two. So another relation between these two is we can form something called a singular complex for a topological space. So what is it? So basically, for a topological space X, we will form its delta complex, or actually, sometimes the literature calls this a triangulation. Okay, so what's this delta complex here? Is for one n simplex, for each singular n simplex here, and then we will attach it in the obvious way. Yeah, just attach it. This obvious way is to make sure that you don't simply attach. Okay, just to make sure that their faces will match. So for each singular n simplex, we just choose one n simplex is enough. Okay, and then we attach in the obvious way. The faces have to match up. And the rest of this junk here is to tell you that the boundary have to match up. Okay, and then the claim is this simplicial homology here is the same as the singular homology. So in this sense that this singular homology can be seen as a special case of simplicial homology. But one remark I want to say is usually this delta complex here, right? It seems to be a larger object than X. A larger object than X. So maybe one thing I think last time we already see this kind of things before is, for example, for S2, right? We can use a few delta 2 to build it up, right? So for example, we can use how many? Maybe we can use 8 of them to build up. And use 8 of them to build it up. Or even 12 of them. You can use 12 of them to build up. Maybe I use different color. Maybe you can use 12 of them to build up. Okay, 6 on one side, 6 on the other side. Okay, so this will provide it a singular, what do you call it? Singular complex. Okay, let's do some examples here. Let's see how useful is it. Okay, let's try some examples. So maybe one of the like topology space, the trivial one you can consider is maybe empty, the void. Okay, so what's the homology of the void here? Okay, because you want to consider map into empty set, right? Okay, so they are nothing. There's no function. Okay, the zero here is not the zero. It's not the zero. It's not a zero map. Zero map is a map. But here, not even the zero map. You understand or not? Here is no map. So it's zero. Zero map is a map. Okay, but here is no map. Some more? I cannot say empty, right? This is a module, right? Module. Yeah. Here is a module. Sure. Okay. So this homology is 0. There's nothing there. Okay, so 0. If there's a 0 map, there's something already. It's very important. So the next non-trivial one is point. Okay. Let's consider a work point set. So we need to consider for every n, what's the continuous map from delta n to this one point. So what could this be? Okay, this is only one map as well. This is a unique map, which is the constant map you can put. Okay, so in this case here, what you get is you will get Z all across. Okay, this is the chain complex you get. I think we also stop at 0 because there's no delta negative. Okay, but what's the differential in this case? Okay, what's the differential now? What's the differential here? Okay, what's the differential here? Actually, doesn't matter, right? Actually, doesn't matter. Doesn't matter? Doesn't matter like what the vertex we apply on. Does it matter? Let me ask you. Does it matter? Doesn't matter. It doesn't matter, right? It doesn't matter, right? Because this is a constant map. They are the same map actually, no matter how you apply. Okay, so meaning what? Actually, you get a bunch of alternating sum. Okay, you get a bunch of alternating sum here. You get a bunch of alternating sum. They are the same map because there's really one map here, constant map, no matter how you restrict it. Okay. So actually, this is equals to 0 if k is odd, and then equal to the constant map itself if k is even. Okay, makes sense. Does it make sense? Because we start with 0. And so if 0 start end with odd, you will have even term. You start with 0 and with even, you will have an odd term. So there will be someone surviving. Okay. So in this case here, what's the map here? So it follows that, or maybe I just label at the top here. So it follows that what you will get is, what's the map you will get here? Either 0 or either identity. Okay. Does it make sense? Okay. Okay, so in this case here, what's the homology? What's the homology here? So the kernel either is 0 or either is Z. But the place with kernel Z, right, is quotient by the image before. But the image before is also Z. So what you get is Hn will be equals to Z at only n equals to 0, because at this place here, the kernel is Z, the image is 0. Okay, so you get hash 0 equals to Z over 0, which is Z. Although I tell people that you cannot divide by 0, but now we only divide by 0. Tell calculus cannot divide by 0, but we divide by 0.
为什么 A 一定
Divide by 0. 只要 second year 就可以 divide 0 了。肯定不一样了 but anyway. Okay, for the rest is 0. Okay, there's no hole actually. Okay, but why n equals 0 have a Z? Because it's path connected component. Okay, make sense? Okay, I think this is the only easy example I can show you. The other example, this space should be quite large, very large. Okay. Not discussed as an example. Okay. Yeah. Yeah, for now, so far, yeah. Sometimes I'll mix some argument from other lecture now. I think that is easier to understand. But we will follow the actual structure. Okay, we'll follow the structure of actual, and then maybe we will just add in more. Okay. All right. Okay, continue. Let's continue. So next is if you decompose your space into half connected component, actually you can also decompose your singular homology, okay, into the singular homology of this path component. And can you imagine how? Can you imagine how? Can you imagine how? You need to think about continuous map from a simplex. So continuous, path connected. So path connected and continuous, what is the relation from general topology? Continuous image of a path connected set is path connected. Okay, so obviously singular and simplex is path connected. So your image must lie in one of these path connected components. So meaning what? Actually, you can split your singular simplex into image in different path connected component. Okay, so meaning we can split the n chain here into the direct sum of this C and X alpha here. Okay, does it make sense? Meaning, you cannot like you cannot split your n simplex, like map one part into different part of path connected component. So one of the singular simplex must map into one X alpha here. So we can split out the singular map. Okay, in this case here, then it's just a matter of understanding this hash and X here. So it's actually you can split out the kernel and image as well. Okay, you can restrict the differential to a path connected component. Okay, so far so good. Okay. Because if you do the big quotient, right, because the image will live in different kernels, so when you take the quotient, right, it will just quotient out the part that's related. Does it make sense? So meaning the quotient on X alpha will only occur because the image of delta and X alpha won't occur in X beta if alpha not equals beta. Okay, so actually you are quotient out by 0 in the other space. Okay, makes sense. Okay, let's continue. There's one more. This one is very important. Maybe we can stop here. Okay, after we learn this, we can stop here. So if X is a non-empty and path connected, then hash 0 is isomorphic to Z. This is what we have been talking about. Hence, for every space X, hash not X is actually a direct sum of Z. One for each path component of X. Okay, so depending on how many path component you have, then hash not X is the direct sum of all these. Okay, let's see how we prove this. So we'll prove the first. Is the second one easy to see? Yeah, second one just follow from the previous proposition, right? Second will just follow from the previous position. Okay, so we just focus on proving one. Everyone can see this second one is coming from the previous proposition because you split into path connected component, but we first proved that every path connected component, the zero homology is Z. Okay, so we prove the first statement now. So by definition, what's the zero homology here? You just take C0x quotient by image of the first partial. Okay, because there's no negative group. So now the answer is we need to understand what is C0 and image of delta 1. Okay, we need to understand what's this quotient here. Or we want to show that this quotient is Z. Okay, how this Z can pop up? There's a trick here. Okay, there's a trick. So we will look at this augmentation homomorphism. Okay, so what's this augmentation homomorphism here? We will just sum up all the coefficients inside this zero chain group. Okay, the zero chain group. I just sum up the coefficient. Okay. So do you know what's going to happen next? Because we want to show that the quotient is Z, right? So meaning that thing I quotient out should be the kernel of this map. And this is our claim. So you should think, how is the image of the delta 1 here get related to this coefficient? You need to think, what's the relation? What's the relation here? Okay. So line. So image of delta 1 means what? The map from a line into X, right? Okay, but you map into a map that map from a point. Okay, so there's a relation about lines and points here. But path connected actually is linking points with the delta one. Okay, so there's some relation here. Okay, so obviously this is subjective because you just take a z and then you send it back to some sigma I. But the claim is the kernel of epsilon is equal to image of delta I if X is path connected. Okay, so to prove this claim, like AA, you want to show the two inclusion of image of delta I is in kernel and then kernel is in delta I. So let's see how do we prove this. So let's show one direction. So one direction from image delta I to kernel epsilon is, since for a singular one simplex here, okay, what do? We just compute lah. You want the image of this to lie inside epsilon, you just compute epsilon on the delta one of some sigma. Okay, but sigma is any singular one simplex here. But what do we do here? What do we do here was delta one sigma, right? We get rid of one of the vertex. So sigma on vi or sigma on v naught. Okay. But what is epsilon map here? Epsilon map here is just add out the coefficients. So one of them is 1, one of them is -1. So they cancel. Okay, algebraic miracle again. This is an algebraic miracle. Okay, next one is the hardest one. Next one is harder. How to show every kernel is image of some delta one. So you need to find a sigma that works. Okay, how to find a sigma that works? Yeah, how to find a sigma that works? Okay, so this is a tricky one. Well, right. So suppose that you have a linear combination, okay, that evaluate to 0. That means the coefficient sum is 0. Okay, so how to build sigma I? So there's some observation here. So this sigma I from this computation, right, are singular 0, 1, 0 simplex, okay, which are the points in X. But then how do we choose a path that works? Okay, so here is how we build it. So just choose from a base point. Okay, just pick from a base point. And then to sigma I of S0, I think. This should be S0. You know this one. Okay. So for each sigma I, right, you pick this tau I. So tau I. Okay. Because there's a lot of sigma I here, right? So you pick a path from some base point x0 to all these S0 here, to all these sigma I S0. Okay, so this is tau I. Imagine the picture. So it's like a spider web. Okay. Make sense? Okay. Then this tau I will be the singular one simplex. Well, we claim that the sum, when you use the same coefficient on this tau I, this is what you will get. Okay, let's check this. So delta of this guy, okay, what is this? Delta of this guy is delta of the sigma I minus ni of sigma 0. So what is sigma 0 here? Okay, what's my sigma 0? So my sigma 0 is the 0 simplex with image S0. So it's the starting point. Okay. It's the ending point minus the starting point. Okay, but this sum here is 0. Correct or not? This sum here is 0. because this sum here is a constant of sigma 0. So actually it's sigma 0 multiplied by 0. Do factorization. Okay, sum of ni is 0. Okay, so you just left with the endpoint actually. Okay, but this endpoint is given by sigma. The map sigma I. Okay, so then this is exactly the kernel term that we started with. Okay. Okay. Okay, so thus ni, we have written this sum of sigma I, which is inside the kernel as a boundary of some singular one simplex. So this shows this argument. Okay, does it make sense? Okay, I think the technique here is to form this tau I. Okay, this tau I here is the important technique. Okay, so then later on, the theory will build on this augmentation homomorphism. Okay, you can think of this as an extension of our chain complex, where this Z is appearing in the minus one term. Okay, yeah. Okay, you can think it as a. So what's the negative one simplex here? Actually, you can think of it as an empty set. Later we will talk about it again, but this is one way to extend our chain complex. Okay, in the negative direction. Okay. Yeah. Okay. And if we extend this, we will get something called a reduced homology. Okay, tomorrow we will start from here. Yes. Yeah. Tomorrow we will talk about how good is this reduced homology. I mean, how useful is it? Not tomorrow, on Wednesday. Okay, see you next Wednesday.
很抽象，
很抽象，没有想过是不是？
是好